Today we are going to be comparing exponential functions, and our objective is going to be to compare exponential functions given in different forms. So we're going to be looking at all the different ways, of writing exponential functions, and different ways of writing them can be useful depending on what you're trying to find. So first we're going to start here with cell division. Humans start as a single cell that divides into two new cells. Each of these cells divides into two cells, and the cell division continues in this way, following an exponential pattern. The time it takes for cell division to occur depends on many factors, including what kind of cells they are. We're looking at these kinds of cells over here that take 1 day to divide. So they take 1 day there to divide. So let T represent the time in days, and P is representing the population or number of cells. So here we're looking at this exponential in 3 different ways. Here we have this first one, of course, is an equation. An equation or model. P of T equals 2 to the T. Here we have our table. Okay, so we have a table, and then over here we have our graph. These are all different representations of the same relationship. Okay, so 2 to the T. So first we want to figure out what is the initial value of the cell population. So we're going to look at that in all 3 forms. So first, to find the initial value would be at time 0. So how many, before they've even divided it all, how many cells do I have? So I want to know at time 0. So an initial value is when T equals 0. So from the equation, I can plug in a 0. 2 to the 0 equals 1. So I can tell I start with 1 cell. Okay. From the table, I look for an input of 1. What's my output? Again, we start there with 1 cell. Now on my graph, I'm looking for an input. Again, here's my time. This is my T. And then my Y is my population. So really we're looking at this point right here. And I will stick with blue. Is the initial time, but it's really hard to tell off the graph. Hard to tell from the graph because of the scale. Your Y's here are counting by, it looks like 100, 200, 300, 400. So a 1 is going to be really hard to tell exactly where that's at. I can tell approximately. I can tell it's really small, but it almost looks like it's 0, which wouldn't make sense. We can't start with 0 cells because then we wouldn't have any cells to divide. So we can't start with 0 cells. So in this case, the equation or the table are better to determine that initial value. Okay. So next, assuming that the cell division never ends, so it keeps going for forever, what is the domain? So that is the set. Again, domain is the set of inputs. The set of inputs, and my input is time, so that would be time. And the range is the set of outputs, which is my Y, which is the population. Okay. So for my domain, time. Okay, so we look at, and in this case, if I look at my equation, I want to look at, well, what values can I put in for T? Well, I can put anything in for T. So if I'm just looking at the equation, we would say the domain would be all real numbers. But we have to consider that the domain is time. Can time be negative? No. Can time be negative? No. So my domain would only be those positive numbers. So my domain, my T, would have to be greater than or equal to 0, because I can equal 0. I can have time of 0. Okay, and then to look, so basically looking at the table to find the domain, it's these inputs. 0, 1, 2, 3, 4. But it depends on what inputs you pick in, because right now we're just picking the whole numbers, but I can have like half a day, a fourth of a day, like I can have part of a day. So here we only picked in whole numbers when really our graph would be all numbers because we can have part of a day. So we look at our graph, it would be, again, time, my X, how far over do I go? I start at 0 and go this way. So my domain would be basically all the positive numbers because time cannot be negative. Now for the range is the population. I can't have a negative number of cells. So my population, which is P of t, also has to be positive, but it can't equal 0. There is no way, and again, remember from our exponential is we have a horizontal asymptote here. It's never going to actually hit 0, and it's never going to actually go negative. So my range is greater than or equal to 0. So in this case, the domain and range for me is easiest to tell from the graph. Whereas the graph didn't do a very good job of telling me that initial value, but it does a really great job of kind of telling me that domain and range. Hey, is P increasing or decreasing? Now, that is kind of to tell from the equation. You look at the base. The base is greater than 1. So that tells me this is growth. So we're going to be increasing. Okay. So if the base, of course, is that greater than 1, I don't have any reflections or anything, it's going to be increasing. From the table, as I put bigger x's, bigger t's in, my function also gets bigger. So as you put bigger values in, so as t goes up, as we go up one each time, this is going up as well. So again, I can tell it's increasing. Now from the graph, as I read it from left to right, my function is going up. So it is increasing. So those are all the different ways of telling it's increasing. Okay, what is the growth factor of the cell population? So here we're looking at the growth factor, not the rate. The growth factor would be the easiest to tell from my equation. Since the base is 2, the growth factor is 2. Okay. To tell the growth factor from this, to tell the growth factor from the table, you look at 2 consecutive points. Like here, this goes up by 1. What do I multiply by to get from 8 to 16? 2. So that growth factor, again, is 2. It's a little harder to tell from the graph because I don't know the exact points of these. But really, you're looking for 2 consecutive, like from 6 to 7. What's it doing? Well, we know it's going from 64 to 128, so it's going up by 2. So again, this growth factor is a lot harder to find from the graph. So the growth factor, hard to find on the graph. This one, that growth factor is easiest. The growth factor is easiest to find on the equation. Easiest on the equation to find. Okay. Now again, this is the growth factor, not the rate. Here, the rate of growth would be the difference between 1. How much more than 1 is this? So I would have to take that growth factor 2, subtract 1. So 1 is my rate, so that would be 100%. It's growing by 100% each time is the rate of that growth. Okay. All right, now task 2. So now we're going to be looking at baseball cards. Some people collect baseball cards just because they like baseball and remember their favorite players. Other people trade and collect them as an investment based on the value of the cards to make money, like certain random, unique cards or very rare cards. So the value of a card grows exponentially. And it can be modeled by here our standard A times 1 plus R to the T. So that's just our standard growth model. A baseball card is taken to 2 different appraisers. They both project that the value will grow exponentially. One projection is given in the table while the second is given in the graph. Which projection has the highest growth rate? Okay, so we just need to determine the growth rate. So that, again, that growth rate, that rate of growth is how much is it going up each time, or how much more than 1 is it? So if we look from here from 0 to 1, that goes up by 1. This one is going up by how much? Again, it's a multiplication. So how much do I multiply by? So I would need to take, let's divide those to find out. So we're going to take that 390, divide it by 300. Looks like it's 1.3. So it looks like we multiplied by 1.3. Let's see if that holds. So to go from 1 to 2, again, that goes up by 1. So let's see, if I take that 390, so if I take that 390 times 1.3, I get 507. Yep, so it looks like that's holding. I'm multiplying by 1.3 each time. So that would be multiplying by 1.3. So my growth factor is 1.3. So if I take that 1.3 minus 1, it goes up by 0.3 or 30% each time. So this is increasing by 30% each time. Okay. Now that's a little harder to tell from the graph. So because they don't give me 2 points in a row. Oh, sorry. They don't give me 2 points in a row. They just give me the 0 and the 2. So we're going to go ahead and we are going to use our standard equation. So our V of t, A times what? B to the t, to figure out that growth factor. I know when I input a 0, when time is 0, my output is a 400. So A times B to the 0 has to equal 400. B to the 0 is 1, so I know my initial value is 400. So I know my equation is 400 times B to the t, right? Now I know when I input, when time is 2 years, when my input is 2, my output is 256. So let's go ahead, let's input A2. B to the second equals 576. So I need to solve for B to the second. So I have to divide both sides by 400. So I need to take 576 divided by 400, 1.44. B to the second is 1.44. So if B to the second is 1.44, B would be equal to the square root of 1.44. So let's grab my calculator again and type in the square root. So second x squared of 1.44, 1.2. B is exactly equal to 1.2. No rounding there, it's exact. So my B, my base there is 1.2. So I'd have 400 times 1.2 to the t. So again, 1.2 minus 1 is 0.2, which is 20%. So this one goes up by 20%, this one goes up by 30%. Which projection has the higher growth rate? Projection 1. Even though this one starts out at a value of $300, this one starts out at a value of $400, this one is gaining value faster. It's gaining 30% of its value every year. This one's only gaining 20% of its value every year. And you can even see here by year 2, this one has a value of 507. This one has a value of 576. This one's almost passed up this one, even though this one started out at $100 more. Hey, task 3. All right, here we have the value of a computer. Depreciates, loses value exponentially over time, t in months. 3 brands sell comparable computer models as shown. We have an equation. So we have an equation for the first one, 485 times 0.9 to the t. We have a table for the next one. And then we have a graph for the last one. So we want to determine the initial value of the computer from each brand and order them from least to greatest. So the initial value. So this initial value is the value at, that should be an E. Value at time 0. So t equals 0. Okay. Well, the first one is an equation. So I can just, and they give it as v sub 1 of t, meaning the first value. So I just need to put a 0 into here. Well, 0.9 to the 0 is 1, so $485. So the first one has an initial value of $485. Okay. The second one, it doesn't give me that initial value. So we are going to have to figure that one out. We'll come back to that one later. This graph kind of gives it to me right there. It's at time 0. I have the 0.400. So for brand 3, this one has an initial value of $400. So the first one's costing me $485. So this is number 1. This over here is number 3, the value of $400. Now we need to come up and figure out, what about number 2? So we know that from 2 to 3, that goes up by 1. What does this go up by? Okay, so we need to find that. What does that go up by? That one's going up by, let's grab our calculator. Again, it's a multiplication, it's exponential, we multiply. So I would need to take the 401.58 and divide it by the 414. So 0.97. So if I take the 414 times 0.97, I get the 401. So I'm multiplying by 0.97. And I knew it had to be less than 1. So if I divided the wrong way, like I was going to, I almost divided it the wrong way. If I would have divided, because we normally tend to do the big one on divide first. If I would have divided the other way, 414 divided by, I typed in the wrong number, 401.58, 57. Why do I want to keep hitting 57? I get more than 1, which tells me that this would be a growth. And it's not. We know it's a depreciation. We know it depreciates, so I know it has to be a decay. Guys, I know it has to be a decay. Okay. So I know I multiply by 0.97 each time. So I'm going to take this table. I'm not very far from the 0 point, 2 and 3. Now, if I was at point 10 and 11, I would probably try to get an equation for it. But since we're at 2 and 3, I guess let's go ahead. Let's do the equation. It's good practice. It's good practice. So our equation would be our initial amount. So v sub 2 of t, I'm sticking with their notation, would be a, was what we're trying to find out, that initial amount, times 0.97 to the t. I want to know, what is it at time 0? Okay, so I need to find out this a first. I know, though, when I input a 2, when my input is a 2, my output is a 414. So if I have a times 0.97 to the second, I get out 414. So let's go ahead, let's work this problem out. Let's take 0.97 to the second. I get 0.94. Why won't it move? Oh, sorry. It was I'm trying to move it and it's not moving. There we are. Oh, I don't know, 0.9409. So I have a times 0.9409 equals 414. So now I would need to divide both sides by 0.9409 to figure out what a is. So a equals, so I need to take 414, divided by, and go up and grab that number, and I get 440.00. So $440. So again, that was number 2. So my initial amount, is 440. So now it says to determine the initial value of the computer for each brand and order them from least to greatest. Which one has the least initial value? Brand 3. So from least to greatest, we've got number 3 at 440, and then we have, 400. And then we have number 2 at 440, and then we have number 1 at 485. All right, our last task. Here we have a cyanobacteria. It's also known as blue-green algae, which we actually do have in South Dakota, if you've heard about blue-green algae. It has the potential to form harmful algal blooms under the right conditions. With sunlight, slow-moving water, nutrients, and the right temperature, populations bloom exponentially. So they end up taking over bodies of water, like lakes. Not as big of an issue in the river because it has to have slow-moving water, and the river moves normally a little too fast for blue-green algae. Under ideal conditions, with a temperature of approximately 27 degrees Celsius, the population P sub 1 of a blue-green algal colony reproduces with a growth rate of 92% per day. So again, that is growth. Okay. An experiment holds a temperature at 20 degrees and records the population of algal cells each day in the table. So this table up here is what happens when it's at 20 degrees Celsius. If both populations start with initial value of 200, what is the difference between the two populations after 2 weeks? Okay, so first I'm going to, under ideal conditions, I'm going to create an equation for under ideal conditions. We start with 200, so there's my initial value. So P sub 1 of t is going to start with 200. It's going to grow at a rate of 92%, which is 92 per 100, which is 0.92. So that's how much it grows by. So 1 plus 0.92 to the t, where t is the growth rate per day. T is per day. So t is in days. Okay, whereas this one, okay, let's go ahead and let's create an equation for this one. So with a 20 degrees, so now 20 degrees Celsius. Okay, it's again, we're starting we'll start at P sub 2 of t. Again, we're starting with 200. I need to find this growth rate from 0 to 1. How much is it going up? So that would be a multiply. So we go from 284 divided by 200. It's going up 1.42. So 1.42 to the t. Now let's double check that. If I take 284 times 1.42, I get 403. Yep, that works. So I multiply by 1.42. What is the difference between the two populations after 2 weeks? 2 weeks is 14 days. So I have my two equations. I want to figure out what the population is at 14 days. Now looking at these, this is 1 plus 0.92. This is 1 plus 0.42. This one is growing at a slower rate. So I should have less on this because it's not ideal conditions. It's not quite warm enough. It needs to be 27 degrees Celsius for ideal conditions. So we are going to go ahead and I'd have 1.92 to the 14. Okay, so let's go ahead. Let's take my equation. So 200 times 1.92 to the 14th power. Holy moly, we get approximately, we're going to round 1850321 point, I don't know, 51. We'll go 2 decimal places. Okay, so that's 1,850,321. Okay. Whereas this other one, P sub 2 of 14, is 200 times 1.42 to the 14. So 200 times 1.42 to the 14. So 276, there we are, approximately 27106.09, approximately. The population, again, these are cells. Look at the difference in just that 7 degrees temperature. So the difference between these two, if I subtract them, take that one minus that one, because it says what is the difference? It's a difference of about 1823215. It's a difference of about 18, what is that, million cells? So that's quite a difference, that just having that slightly 7 degree temperature change has.